Hi, I'm Buttfield-Addison and I'm an iOS developer and game designer at Secret Lab. I've written a whole bunch of books for ORELLY Media, and I most recently released the Practical Artificial Intelligence with Swift book. I'm talking to you today from the beautiful city of Hobart, which is in the state of Tasmania in Australia. Machine learning has a reputation for being quite impenetrable and a little bit scary at times. It's full of fancy words like activation function, tensor, generative adversarial networks, mini batch stochastic gradient descent, and many more. It has a reputation for being very mathematics heavy, and if you don't have the background, that can drive people away. It doesn't really need to be like this though. The vast majority of amazing machine learning power features can be built without having to understand too much about what's going on under the hood. You don't need to have a deep understanding of the underlying technology as long as you know the goal, what you're trying to accomplish. This is an approach called task-based artificial intelligence. There are certain tasks that machine learning is really quite good at. For example, image recognition, recommending things, sound classification, dictation, and other tasks that until reasonably recently were considered to be things that only human beings and their squishy organic brains could do. These tasks are now achievable on small-scale devices like mobile phones through the application of amazing technologies like deep convolutional neural networks and other words that give people who are scared of maths, like me, cold sweats. But again, we don't care about how the results are achieved, only that results are achieved in the end. The idea behind task-based artificial intelligence is that you can build systems on top of existing, much more detailed and much more technical machine learning infrastructure, which is designed to support very specific practical tasks. You don't actually care how the system is performing image classification, for example. You just care that you can feed it images and it can give you results. Knowing more information about how the machine learning system is forming this classification and generating results is absolutely useful, but you don't need it anymore, and you don't need it until the time comes for tuning and improving the accuracy and efficiency of your systems. Until you're at this point where that becomes important, you don't need to care about the underlying implementation at all. It's an amazing time to be building machine learning features. The machine learning technologies and frameworks that come with Xcode support this style of building machine learning into applications. While all the underlying stuff is still exposed if you want to make use of it, the tools also provide you with applications and frameworks to make straightforward and simple machine learning models that you can use straight away for common tasks. We only have a short amount of time together today, so we're going to take a look at two different kinds of machine learning features, what I call big features and small features. First, big features. These are the kind of features where you build an entire application around the thing. For example, apps that take an image and use a complex filter to convert it into an entirely different kind of image, or you want to make an application to identify music. For example, Shazam, the music detection and classification application that Apple recently purchased, records audio and then identifies songs that are being played in that audio. The entire application exists to present this feature to the user. It's a big feature. The other kind of feature is what I call small features. Small features are where you use machine learning techniques to improve a facet of an application that you're building. For example, the built-in spell checker and autocorrection tool is able to identify domain-specific terms such as iPad, iPhone, AirPods, Apple Watch, and so on. Another example of a small feature is the face recognition system built into the Photos application on Apple's products. The cool functionality of the Photos app is to manage the content of your photo library, but it also has machine learning built in to identify faces of the people in the photos. This improves the overall experience of the Photos app, but the entire application is not built around this specific feature. It's a small feature. Today we're going to look at both a big and a small feature. We're going to build an entire application built around a single task using machine learning, and we're going to add machine learning to improve a larger application. As part of this, you'll learn how to use the existing machine learning developer tools that are already on your computer and how you can get started with them right now. We're going to be using some common tools that are built in, and we're also going to be using stuff we download and install. First, we're going to use Xcode. Everyone knows what Xcode is. It's the standard software tool for building software on Apple's platforms. We're also going to be using coreml to train and export our model. I'm sure you all know Xcode. I'm not going to explain it in detail, and there's a lot of great resources available on Apple's website if you're not familiar with Xcode. However, coreml. coreml is amazing. coreml is something that you might be less familiar with. coreml is an app that simplifies the creation of machine learning models used for common tasks. So you can pick what you want it to do and you can do it straight away. You can create models that perform image recognition, text classification, as well as more generic tasks like recommendation. You simply choose what kind of machine learning task you'd like to perform. coreml asks you for some training data, and coreml then generates a model. It performs validation and testing of the model as well, and it's really good for the task we have in mind today. It comes built in with Xcode, and it requires macOS 10.15. Most machine learning projects with coreml follow the same process. There's a model, you give the model some input, and it gives you some output. Depending on the model, a whole bunch of different things could be going on under the hood. For example, when you build an image classifier with coreml, it builds a model out of layers of convolutional and pooling layers, performing feature extraction, then using classifier layers like softmax. This is just one way you could build an image classifier model. Apple could change how coreml does it in a future release. The joy of this is you do not need to worry about it. coreml is a beautifully simple tool that breaks down the process to supplying the data, checking what it outputs, and then using the model in your app once it's working the way you need it to be. You do not need to worry about the model construction. It's there if you want to, but you do not need to think about it. You don't need to worry about how transforms to calculate the power spectrum of the sound when you're doing sound classification happen, or that you're running your sound through a filter bank, applying multiple triangular filters to extract filter bands. You just ask for a sound classifier. It's an incredibly useful, practical approach to machine learning that means you can build features for your apps that use machine learning without getting bogged down in the details. First thing we're going to do is build an application that can classify sounds. It will be able to listen to the outside world and identify what type of animal it heard in some audio. Once it's determined what kind of animal we are listening to, it will then show an icon on the screen representing that animal. There are a few things we have to do in order to build this application. First, we need to decide what kind of task we're performing and see if the existing tools we're working with can handle this. Next, we need to acquire a dataset that we can use to train the machine learning model. We'll then need to prepare the data, train the model, and then build the application around that model to feed it data. The model will then give us back results. This specific kind of tasks we're trying to do is a sound classifier. Given a chunk of recorded audio, we want to feed that audio into a classifier, get back a set of results. Each of these results will be the type of sound that we have identified and how confident we are in applying that label to the recording. To build a model, we need to decide on what possible labels we want to apply. For this application, we care about animals. We'll come up with a list of animals that we want to train the model to recognise. One side effect of this is that if you have any audio of other animals, we won't be able to recognise it correctly. In fact, it will mislabel that recording as one of the animal types we specified. There are ways to work around this, but we'll accept the limitation in this demo. This model will only recognise sounds that it was previously trained on. So this means that whatever kind of data it has during training will form the list of possible labels that we can apply to the incoming audio. This is why it's very important to have a large and diverse training data set, and it's also the reason why large companies like Google and Apple spend a great deal of effort and money collecting human-verified data. If you've ever completed a CAPTCHA hosted by Google to verify you're a human, you've provided them with some human-verified labeling information for data. This is why those kind of tests generally include tasks like identifying street signs or vehicles. It's for training object classification and object recognition in machine learning models. We don't have time to put together our own training data set today. Because it's a fairly large task, I'd have to record hundreds and hundreds of animal sounds. Fortunately, there are many datasets out there that we can make use of. One of these is ESC50, which is a labelled collection of 2,000 environmental audio recordings taken from the Freesound project. These recordings are of things like animals, humans, nature sounds, and much more. To get started, I've downloaded the dataset from GitHub. It's about 850 megabytes. Once you've downloaded it and unzipped it, keep it somewhere. We won't be using all the data, just the animal noises. The full dataset is actually licensed under the Creative Commons Attribution Non-Commercial license, which means you can't use it for commercial purposes. And they have a smaller 10-label dataset that is licensed as Creative Commons Attribution. Now that we've downloaded the dataset, we need to prepare the data for coreml to work with. coreml expects the files to be sorted into folders, and each folder becomes a label for those files. For example, all the recordings of dogs need to be in a folder named dogs, all of the cats in a folder named cats, and so on. This requirement is documented in coreml's documentation for each thing it supports. I've moved the files into a folder that matches their label. If I open the cat folder, all the files are recordings of cat noises. Great cat noises. Now that we've prepared our data for training, we're ready to create the model using coreml. Open coreml by opening the Xcode menu, choosing the Open Developer tool, and then choosing coreml. You can also just search for coreml on your computer. Click New Document and then choose Sound Classifier from the list of templates. Click Next and save the project somewhere. Next, select the model source from the list on the left-hand side of the window. Open the drop-down menu in the training data and select Files. Locate the classes folder that contains the specific set of animal sounds that we want to use. This is our dog folder, cat folder, and so on. Then click Open. coreml will identify how many classes there are, and it will split the files into a training set and a validation set. We can provide our own validation set if we want to, or we can leave it set to automatic. In this mode, coreml will divide the training set into two datasets randomly. It's about 80-20 split. coreml will detect that you have the 10 labels and a total of 400 items, and we're now ready to train. Click the train button, which is the play button, and you can watch as coreml trains the model. It will first start extracting features from the audio, and then it will begin multiple iterations of training. For a small dataset like this, it won't take too long to train. On my machine, which is a MacBook Pro, it takes about 2 minutes to finish. Once it's done training, you can take a look at how well the finished model performs. coreml will show what percentage of the training and validation data the model was able to correctly recognise. We can also run tests on the model by providing it with additional labelled sounds that the model has never seen before to test. The model is now ready to use, and we can drag the file that's outputted into a folder. Before we start working with the trained model, let's look at the base application that we're going to put the model in. The app has a collection of icons, one for each of the 10 types of animal that we can recognise. When we tap the record button at the bottom of the screen, it will record a few seconds of audio and save it to a file. The part that's missing is the classification. We want to give the recorded sound file to our machine learning model and ask it to give us back the type of animal it's decided to label it as. Once we have that, we'll highlight the corresponding animal icon. First thing we need to do is add the trained model to the app. I'll do this now by dragging and dropping it from the folder I put it in. coreml model is just a data file. In order to use it in our app, we need code that can open this file and work with it. Fortunately, Xcode generates most of this for us. This generator model class, which is not intended to be changed unless you know exactly what you're doing, allows us to feed inputs in and get outputs back. We won't be using it directly because we'll be using the sound classifier classes that provides to make it easy to take audio data and get back results. That said, it's worth looking at the code that Xcode generates because it's useful to understand how the model works with the rest of your code. There's also a great book called the coreml handbook that will tell you exactly what's going on. Sound isn't an instantaneous thing. It's something that happens over time. If you're analysing live audio, there's never a moment that the analysis is finished and generated a single result. Because of this, the sound classification libraries that come with coreml will actually generate multiple results over time when you give it audio data. We now need to think about how we provide audio data to the model. coreml models work based on requests. When you want to give data to the model, you create a request and submit it. After the model has been run, you get back results and requests. Each result contains two important labels in this case: the label the model wants to apply to the data and how confident the model is about it. To get results, we'll create an SN audio file analyzer. This is a class that takes a file and notifies another object about the results that it's seen. This other object is called the observer and receives the results as they come in. It's also notified when the analysis is complete. The observer conforms to the protocol SN results observing. When a result arrives, the method request did produce result is called. Each time we receive a result, we'll keep it. If it has a reasonably high degree of confidence, when all the data has been analysed, we'll look at the accumulated results and let the application know which result we're most confident about. This will be used to indicate which animal icon to light up. Let's get started adding the audio analysis features to this app. I've created an empty file called audio.swift, where I'll put all of my analysis code, so that I don't need to touch the view controller code very much. I'm not cool enough to use SwiftUI yet. I'll start by importing coreml, AV Foundation, and sound analysis modules, which contain the classes I need. Next, I'll create a new class called Audio Classifier, which manages the ML model and the sound classification code. It will instantiate the model class as well as a sound classification request that uses the model. I'll rename the ML model to something easy, so like Animal Classifier, so I can call it from the code. Notice that the classification request has a try. That's because initializing it might fail if we used a model that wasn't designed for audio. We also need to create the results observer class, which will receive information from the model and store the results. We have some important methods to add. First up, we'll write the request did produce result method, which will be called every time the analyzer produces a classification result. It will take the result, check to see if it's confident enough, and if it is, it will store it in the results array. Next, we'll write the request did fail with error method. As you might guess from the name, it's called when the analyzer fails. When this happens, we'll return a nil result to the rest of the application. Finally, we'll add the request did complete method, which is called when we're all done with the analysis. In this method, we'll select the label that we have the highest confidence in and return that to the application. Now that we've written the request observer class, we can use it. We'll go back to the audio classifier class and add some code that creates an audio file analyzer and gives it an audio file to recognize, as well as a request observer to notify when it gets results. We'll create the analyzer, add the request, and then I'll tell it to analyze. That's all of the machine learning code that we need to do. Now we just need to attach it to the user interface. We'll go back to the viewcontroller.swift file. We don't have much to do here. First, we'll create an instance of the audio classifier as a property. Finally, in the classify sound method, which is called when the recording completes and receives the URL to the audio file, we'll take the string that we received, convert it to an animal, and then let the view controller know. And we're done. We need to clean up a little bit of my code because I made a small mistake because I've been locked in my house for several months. We're going to go back into audio.swift, remove the throws from the init and add an exclamation mark after the try, just so we can make this run. And now we'll build and run the app. Perfect. It can detect cats and pigs, and probably the other animals as well. We could improve this by making it do analysis live on various samples of the audio, and you can find that in the code repository. Now that we've built an app around a single machine learning feature, let's look at how we can use machine learning to improve a larger app. While it's interesting to build a cool toy that shows off the power of coreml, machine learning is at its best when it's improving the user experience of an app. So, let's improve an app using machine learning. I'm about to launch my amazing, brand new and totally original social network site. It's called Birder. On Birder, users can post chirps, which are short messages. The short messages can have images attached. It's a very original website. It's really important that my app be accessible to users with limited vision, so I'm designing Birder so that users can add captions that describe images that they're posting. This is important for screen readers, who will use the caption when reading the text to their user. I've already added the ability to take photos and add captions. If I launch the app, take a photo, or pick a photo, I can type a description of what's in the photo. But it's easy to skip that step. I could just make it mandatory, but it's important to remember that the more steps you add increase friction, and we want to make this as accessible as possible. Another idea is to use machine learning to get us part of the way there. We can use coreml to do object recognition on the photos that we add, and use that to create a starting point for our captions. This doesn't mean we're absolving users of the need to add descriptive text, but it does reduce the amount of work they have to do. There are two common types of image analysis: object classification and object detection. Object classification models attempt to classify the dominant object in an image, while object detection models attempt to identify multiple objects in an image. Classification models answer the question, what object is this an image of? While detection models answer the question, what's in this image? It's a subtle difference, but it's important. Because we want to answer the question, what's in this image, we'll use a classification model. A good one is the YOLO v3 Tiny. YOLO in this case stands for You Only Look Once. It was developed by Joseph Redman and Ali Fahadi. You give it an image and it returns information about which regions of the image contain an object that it's recognized, and a possible identifier for those objects. It's called Tiny because it's designed to be very small. The model is only 35 megabytes, and less accurate ones are even smaller. This means you can ship it in very small iOS apps. A pre-trained YOLO v3 Tiny model is available to download from Apple's coreml models site, which is incredibly useful. I'll go ahead and download that now. Because we're generating captions for our images, we don't really care about where the objects are in the image. We just care what they are and whether they're in the image or not. This means that we're being slightly inefficient with our use of this model, but it's fine for this demo. Let's get started adding object detection to Birder. We'll start by adding the downloaded YOLO v3 Tiny model to the project. You can see here that YOLO v3 Tiny has a bunch of inputs and outputs. So the inputs in this case are an image and a bunch of other stuff that we don't necessarily need to worry about right now, and its outputs are a confidence and a set of coordinates. We're going to open the post-chirp view controller file. In order to submit images to the model, we need to process them. The model is expecting a 416 by 416 square grid of colours, but images that come off the camera will be much bigger. They need to be scaled and cropped. Fortunately, iOS makes this very easy. There's a framework that does it. It's called Vision. I've already imported it at the top of my code along with coreml. We deliver images to the model by creating a request. A request delivers information to a model and calls a completion handler when the model has finished processing. The request also has properties that let us set up how the image should be delivered, like how it should be scaled and cropped. The observation request uses a coreml model class. In this case, we'll use the YOLO v3 Tiny class that Xcode generates for us. It also uses a completion handler, which is called when the request generates a result. For this app, the completion handler will call the process observations method, which will use results to generate and display the caption. Now that we've set up our request, we need to use it when the user takes a photo. My code has already been set up so that when an image is taken, it calls image was captured. At the moment, all it does is display a placeholder caption. To use this image with the request, we need to create a handler and ask that the handler perform the request. We'll take the image and use it to create a handler. We also need to get its orientation because the handler uses that information to make sure that the image is sent to the model the right way up. Finally, you might notice that we're doing all of this on a background dispatch queue so that the user interface thread doesn't get blocked while the model is working. When the request is completed, process observations will be called. When process observations is called, it receives an array of results, or an error. To use the results, we cast the array to VN recognized object observation objects. This is a safe operation because the model is guaranteed to only return results of this type, and then we can use the results to produce the caption. Each result represents an object that the model detected in the image. The model can recognize 80 different categories of object, and for each result we get the confidence for each category. What we want to do next is select the label that has the highest confidence. We also only want to use that label if we're at least 80% confident in it. This means that if we take a photo and none of the objects have a label with enough confidence, then we won't generate a caption. It's better to give no result than give a bad result. We're all done. Let's launch this app and see what happens. So now I'll say I've got a really nice vase, or as Americans say, vase. I might want to post about it. Look at my really cool vase. I put a plant in it. I pick a photo and I pick my really cool vase. Now my caption's automatically generated for me. May contain vase. That's amazing. Or I might get some cars. Look at this. I am so rich that I have 3 cars. I'll pick my cars. It says, well, it's detected 2 cars, so that's pretty good. So we've got captions being generated in enough detail that they're fairly useful. So it's important to remember that machine learning isn't a shortcut. It's not a substitute for having a human being in the loop. When we generate our captions in Berda, we make sure that the user has a chance to edit them. I did cars, it said car, so we want to improve it before we get posted. Machine learning technologies are not really performing cognition. They're generating automated results that don't take into account any positive or negative impact on people. What they're really good at is getting you part of the way there at very low cost and scale. To see what I mean, let's compare a human to a machine learning system. When it comes to image recognition problems, you'll see what I mean. When it comes to speed, a human is slow, a machine is fast. When it comes to cost, a human is expensive, a machine is cheap. And when it comes to scalability, hiring more humans is very slow, but spinning up more machines is very fast. So much for humanity. But it's not all good news for the robot overlords. When it comes to bias, a human has lots, but a computer has more due to it being a lot less flexible after training. Decisions at training time are encoded, and it can only recognize classes that it was trained on, far less than is available to a human. For quality, a human being is generally excellent, regardless of educational level, while the machine is kind of okay on average. Finally, people are affected by the decisions that are made based on a result, while a machine isn't. This fact alone means that purely AI-driven decisions are an absolutely terrible idea. Machine learning-based solutions are at their best when they're used to get a task part of the way there and let a human be the final judge. Today, we used coreml to train the custom model that we made. But there are other tools. Apple ships a Python library called Turi Create, which replicates much of the functionality of coreml, but in Python form. Turi Create lets you integrate your machine learning workflows into more traditional maths-heavy ML tools, such as TensorFlow, PyTorch, and Keras, which are all, perhaps obviously, Python frameworks. Turi Create also follows a task-based approach to AI, and supplies pipelines to create recommendation systems, image classifiers, text classifiers, drawing classifiers, sound classifiers, object detectors, neural style transfer models for giving images the style of another image, activity classifiers for determining what sort of motion is occurring from device motion systems, as well as general classifiers for predicting a label from a generic set of data. It also has regressors and clustering algorithms if you want to get more generic, as well as a whole API for loading very large amounts of data from a disk without filling up your RAM. Turi Create is really powerful, and it's almost as easy to use as coreml, but it is Python-based. It also supports Linux and mass training models across GPUs and other such useful features, but if you're looking for a pure Swift experience, you'll need to go elsewhere. If you're keen to try it out, there's a really good WWDC 2019 talk on it. We recommend you check it out. Alongside coreml and coreml, Apple also ships a few other machine learning-focused frameworks. Vision, which we use today, focuses on visual tasks around analysing images, and sound analysis, which we also use, does likewise for sound. There's also the speech framework, which provides easy-to-use APIs that use machine learning to convert audio to text with absolutely no model required, and natural language for processing and working with text. Apple even ships two much lower-level APIs, Accelerate and BNNS, which are machine learning-focused maths libraries and a basic set of APIs for constructing neural nets, respectively. There's a lot to learn, and it kind of goes beyond the task-based practical focus of this talk, but it's really cool if you get interested. You definitely do not need to explore beyond vision, natural language, speech, and sound analysis if you just want to focus on task-based machine learning. You can build speech recognizers, text classifiers, custom fuzzy matching learning recommendation systems, sound and music analysis tools, activity classifiers for exercise, and everything in between, using the supplied task-based, task-focused frameworks. Most problems in this area are solved by combining coreml, the general framework for talking to coreml machine learning models, with one of the specialized frameworks, such as vision or sound analysis, for analyzing the specific domain your model is in. CreateML and Turi Create provide the bulk of what you might need to train your model, and there's plenty of models in Apple's model page, which is where we got the YOLO model earlier, as well as various other what are called model zoos, if you want to get creative and mix and match. While we focused on using coreml models today, frameworks like Vision also provide features that don't depend on you providing a trained model. The facial feature recognition system built into Vision uses recognition techniques that predate the recent boom in machine learning, and it works really well. This means that you often don't need a model at all. Apple provides built-in, heavily optimized support for detecting faces, as we said, but also features of faces, such as the nose, mouth, eyes, and so on, as well as animals, speech in a variety of languages, parts of speech, verbs and nouns and such, and features of language, such as places and people's names and organizations and things like that. And it can also identify the language a piece of text is written in. You don't need a model to do any of this. You can also train very small models that augment Apple's text system, allowing your app to offer spelling and autocorrections for names and words specific to your product or domain, by building an NL model, which is a custom type of coreml model focused on text. You can, of course, combine coreml with Apple's other frameworks, like ARKit, to perform live recognition and tagging of real-world things right through the camera. I'm sure any hypothetical future AR hardware from Apple will be an amazing experience for machine learning products. All of Apple's tools emphasize tasks over algorithms, but you can usually get down to the metal if you need to. One of the ways you can do this is by using machine learning tools that exist outside of the Apple ecosystem and using them to train models that you can convert to coreml. The models that we use today came from CreateML, or were downloaded from Apple's site. They're already in the ML model format that the coreml framework expects, but not every model you'll encounter is in this nice, convenient format ready for you to use. There's no magic to this format, it's just the format that Xcode understands, which allows Xcode to tell you what the inputs and outputs are of the model. There's absolutely no magic to it. Every machine learning model is fundamentally very similar. Some models require a very specific training pipeline, which tools like CreateML and Turi Create can't supply. To help with this, Apple ships coreml-tools, which is another Python framework supplied by Apple for converting models from other popular machine learning pipelines into coreml. It supports bringing models from TensorFlow, Keras, and many other frameworks. If you find a great model online in one of the many model zoos, and it's not in coreml format, chances are you can make it work with coreml using coreml-tools in Python. If you want to deep dive into how and why coreml works, we highly recommend the Coreml Survival Guidebook. It's so good it should be part of Apple's documentation. Naturally, we're also very proud of our book, Practical AI with Swift, which teaches you step-by-step how to do a wide range of activities from a task-based practical perspective. In this talk, I hope I've given you a little taste of what you can do with these technologies and gotten you excited to apply them in your next app. You can follow me on Twitter at ParisBA, and I'd love to hear from you about what you think. I'll tweet out a link to some more resources. Thanks everyone for coming, and feel free to tweet me your favorite examples of machine learning when it's really interesting or hard to notice that it's machine learning. My favorite example is the instant alpha feature in all of Apple's apps that uses machine learning to find edges and just makes it feel like it's magic. Thanks everyone.